I don't know that one.
Hey Alexa. Alexa. Pretty cute. I need this? Why do I even have it to anthem? I wanna feel good. I wanna feel good. I wanna feel good. I wanna feel good. That's my water bottle. Hey Alexa, pause music. I haven't even finished freaking queuing delay.
If the traffic intensity is 1, then delay will go like exponentially high, and it becomes in. You should not try to even overflow. So I've already physical link. If you increase the physical link, you increase the propagation delay, right? So now everything puts into the picture. There's no need to talk about this. It's just an analogy, but I think it's very clear to you. This analogy is overflow. So overflow in our 8 times L. It could be removed in the next version of the paper, I don't know, but in some countries they still have that, but don't worry too much about that. Let's move right into some real examples where we can explain the queuing delay, because remember in the beginning I said the formal word for buffer is queuing, and we have this mathematical tool because we have theories to explain the behavior of the queue. So if your packet is waiting in the buffer, and if you have some statistical information in your hand, then you should be able to use queuing theory to quickly understand how much, expected delay you have in the system. However, we are not going to go into real queuing theory, but I'll just show you a graph that came out of the queuing theory, right? So queuing theory will not be part of this introductory computer networking. So you're kind of off the hook, but you have to understand the behavior. So packet length is L bits, right? And arrival rate is A packets per second. So number of packets that's arriving statistically on average to the queue is A, and the link capacity is R bits per second, right? So we have three parameters, and we are trying to understand the queuing behavior for this scenario. So the question is, what happens if A times L? So what is A times L? The A packets are coming per second, so you're trying to find out how many bits are coming per second. So A times L, AL is the arrival rate to the link, right? And R is the draining rate of the link. So if the arriving rate is greater than the draining rate, what can happen? What's the obvious thing that will happen? Overflow, yes. So in a bucket, you have a hole in the bucket, so the water can go down. But if the water is that you're pouring in the bucket at a rate higher than the draining rate, or in a basin or somewhere, then you will see that it will overflow. So overflow in our case is loss, packet loss. So this is very obvious. So this is not the problem, right? The thing that we want to study is more subtle. It's here. Okay, so the first scenario that we want to study, so pay attention to these scenarios, right? So this is the first scenario. What is the first scenario? One packet arrives every L over R seconds. So the packet arrival process is not random. It's deterministic. Every packet arrives exactly L over R seconds later. Right? So this scenario, although you have A packets that are arriving per second, because every packet is arriving L over R, so your arrival rate is still like R over L packets per second, right? So what is traffic intensity? Traffic intensity is the arrival rate divided by the draining rate. That's the intensity. If it is 1, in this case this is 1, it means the arrival rate is the same as the draining rate, and you do not expect any problem, right? Intuitively. And indeed, we do not have a problem here. If the queue was initially empty, when the first packet comes in, then it takes L over R seconds to clear the packet over this link transmission, because it has a capacity of R. And you know that there is no packet arriving in L over R. So you just clear this packet, and the second packet comes in, and it's ready to be transmitted. So you don't really need a queue, right? Queue doesn't build up. And the queuing delay is 0, right? So it looks like, oh, okay, so if your traffic intensity is 1, then there is no queuing delay. But this is not true. In fact, you will soon see in the next slide, you should never design a computer network with traffic intensity 1. You should not try to even get close to 1. Why? That's the second scenario, which is the realistic scenario, which is the practical scenario, which is what you are doing right now. This is random, right? Firstly, traffic. They are not deterministic, right? When you hit a website or a link, lots of packets will come at the same time. Back to back, right? So if you have n packets coming back to back, it means simultaneously. Then there's no way that this link will be able to transmit all the packets at the same time. It will just take the first packet, while it's transmitting the first packet, right? The first packet has no problem, 0 queuing delay, because it doesn't wait in the queue. When it comes, the queue is empty, so it goes straight into the transmission link, right? Transmission link has its own buffer for one packet, and it transmits bit by bit, right? But it doesn't wait in the queue here. But the second packet, right, has to wait for the first packet to be finished. One packet takes L over R transmission time to be transmitted. The third packet will have to wait 2 times L over R because there are 2 packets in front of it. The fourth packet will have 3 packets in front of it. The fifth packet will have 4 packets in front of it. Right? So if you add up and you use this series, then you will at the end, you will find out that it's L times n minus 1 over 2R, the queuing delay. Right? In this particular case, queuing delay is not 0, but it is significant. And if n is very large, a lot of packets come at the same time, then the queuing delay can be very large. Right? But interesting thing is traffic intensity is 1. Remember in the previous slide, traffic intensity was also 1. So what is the problem? Traffic intensity is still the 1. It means, on average, the arrival rate is equal to the draining rate. Why do we have a problem? That's on average, but temporarily it's overloaded. That's why you need a buffer, right? We have seen that before. But now we are looking at that more mathematically. And as you can see, the traffic intensity 1 is not necessarily good. And in fact, why it should be avoided? This graph is from queuing theory. So in queuing theory, you can explain, and at the x-axis, you have the traffic intensity. And in the y-axis is the queuing delay. So this is so fundamental in queuing theory. So in queuing theory 101, that's what they tell you. If the arrival is random, like the delay between 2 people or packets or job coming into the queue is exponentially distributed, then they can quickly solve a closed form solution for the expected queuing delay. So this is plotted from that expected queuing delay, and they show you if the traffic intensity increases, then look at this. This is non-linear. And the delay increases rapidly as you approach the traffic intensity 1. And that's why I said a few minutes ago in the previous slide that you should never design a computer network with close to 1 traffic intensity, like 100% utilization of your link. What is 1 traffic intensity? You want to make 100% utilization. So you have deployed the 1 gigabit per second transoceanic fiber optic, and you are paying millions of dollars, right, in leased fee. And you say, oh, I will design my network so it's always busy. This is what's going to happen. If your link is always busy, it means the traffic intensity is 1, then the delay will go like exponentially high, and it becomes infinite, right? So do you buy this? Do you understand it?
What the
You don't
frick?
need to know the queuing theory, but you have to be motivated. You have to accept this. And if you have any questions, just let me know. Yes, we have a question. The queuing delay is the delay time, yes, but this delay is affected significantly by the traffic intensity. As the intensity approaches 1, the delay grows exponentially. N divided by, so each packet, so it has L bits, and the link capacity has R bits per second. So a packet takes L over R second to be transmitted. Which one? Is it here? Is it here? Previous slide, right? 95, did you say? 95? This one? Okay, so yeah, okay. Okay, the question is, how did I get this R over L packets per second? So the arrival rate, if you go back even one slide, I said that the arrival rate is I am getting A packets per second. Okay? So you are getting A packets per second. So arrival rate is A packets per second. And you will see that each bit, but this packet, sorry, this is not 8 packets per second. This is 1 packet arrives. So 1 packet arrives every L over R seconds, right? So 1 over LR will give you the time for how many packets that are coming per second, right? Yeah.
Like going 8 kilometers for 2 hours. 8 kilometers.
Yeah. Yeah. Okay, any other questions? Right. What we want to do next, if you agree with this nodal delay, remember that we were interested in end-to-end delay, so this is the end-to-end delay. So when your packet is traveling through the network, which is a network of networks, it means that you are going through multiple hops. You are going from one router to the next link to the next router, and until you reach the destination. And it means you have to add up all these intermediate delays so that you can get end-to-end delay, right? So here is another example to show you how you are experiencing delays in your network in different links. So this is your client. You are connected to this router. V1 is the distance between here to here, V2 is the distance from here to there, and this is, so R1 is,
Why is SDK bookmarked? What the frick? This is a mission rate versus transition rate. When bursts past 500, you'll let the internet run for a very long time. You'll eventually see that the queue fill up and overflow. Indeed, when two rates are the same, that is because one, the queue grows without bound, with random inter-arrival times as described in the text. Entering is it the transmission rate? What do they call it in the lecture? starting to queue up. Why is it called arming? case where packets are arriving. Okay, cool.
Is the rate, right, of this link, the speed, the link capacity, if you like. This link has a different capacity R2, and this one is R3. But in this case, let's assume R1, R2, R3 will be the same in this picture. And then you can say packet length is L, propagation speed is S, right? So let's look at this picture. How do we explain this picture? You can see the client started here, so it transmitted the first bit of the packet, but the first bit took this long, D1 over S, this the distance, the propagation to reach here. So just because you transmit it here, it doesn't arrive at the same time. There is a delay here. That delay is that propagation delay affected by the distance, right? And you send the first bit here, this is the time axis, and the last bit here, because there is a link capacity, and you cannot put the first bit and the last bit of the packet at the same time. It's not a parallel transmission, it's a serial transmission. So there's a delay, and that delay is affected by the transmission speed of the link, the capacity of the link, and the size of the packet. So you see L over R1 it takes. So the last bit of the packet arrives here. So when the last bit arrives here, this router will start processing. Very small processing delay, right? And there is no queue in this router, as you can see.
What is he talking about?
Queuing delay. After the processing delay, it decides to transmit on this link. So again, it does the same thing. And when
What? You just stop talking.
Yeah. Let's use this one. Let's introduce queuing delay in R2. So if there is queue in R2, then it will take a long time before it gets this packet because it's waiting in the queue. Right? So what we see here is that if there is built up queue in one of the hops, that hop will experience longer delay than the other hop, as you can see. So there's a long queuing delay, and then it starts to transmit. So your end-to-end delay starts from the moment the client transmits to the moment it's received. In between, there is so many different kinds of delays happening, including the transmission delay, the propagation delay, and now the queuing delay in one of the nodes. Yeah, so good question. It depends on the scenario. So if the transmitter is a supercomputer because you are trying to download a file from a supercomputer, then usually the supercomputers are connected with gigabit per second links to the internet ISP. They pay a lot of money, or the big Google servers. So if the packet is 1,000 bits or something, then it's insignificant. But if you're downloading from a huge data center from the US, then the propagation delay becomes the bottleneck. Yeah, that's also possible. So if you are using a mobile phone and not the iPhone 14 Pro Max, and you are trying to read something from a very high capacity server, then the bottleneck is actually in your operating system, in your machine. I think in lecture 7, or yeah, lecture 5 or 7, we'll start looking at TCP as a transport protocol end-to-end managing. So in those cases, what happens is that that big server can easily overwhelm the small machine, and a lot of packets can get lost right in your buffer. They arrive, but you can't process them, so they get lost. So to prevent that, there is an automatic protocol, TCP, has a mechanism to tell the server to slow down. So whenever there is a bottleneck, we have protocol mechanisms, either at the transport layer or at the link layer, to adjust the rates or some other things so that the packet loss is minimized. Okay? Any other questions from this slide or anything that's bothering you or you're curious? You don't have to stick to this slide. You can ask anything. Okay, so these are like traceroute and other lots of commands that you can use to do actual experiments to find out for some specific source and destination what sort of delays you are experiencing, where the delay is coming from, where is the bottleneck in this long route and things like that. So these are the topics of your laboratory hands-on experiments. So you can actually experiment and relate this theoretical knowledge that you learn here about these delays and put into real thing in your report. So you have to do all these experiments, collect the data, and write a report and submit the report when you complete the lab, right? One of the things you will find out when you do the lab is that these delays are not constant or are not deterministic. They vary a lot because of the traffic in the internet is so dynamic, especially these days because we are mixing voice, video, data, all into the same router in IP packets. In the old days, it was only data. And voice and video were going through telephone or TV network, and now Netflix and everything is here. So packets are being mixed, and the delays are statistically. So you have to look at the standard deviation of the delay and things like that. So when you do your lab, you have to report what sort of, so here is the cumulative distribution function. So you have to plot these kind of things and submit your report and reflect on what you have done. So a very quick quiz question just to see. The propagation delay depends on the size of the packet. Is it true or false? I didn't hear it. False. Yes, correct. Propagation delay is the speed of light, but it does depend on something. What is that? Distance. Yeah, very good. Okay, so let's do another quiz. Slightly tricky. It's not tricky. So what we have done, we have understood very well, it looks like from your response, what is transmission delay, what is processing delay, what is propagation delay, what is queuing delay. It seems that you understood each of these components very well. What we are asking is about the sequence at which these delays are experienced by a packet when it goes into a node. So can you put together the sequence? So who would say the answer is A? A means that the transmission delay is experienced first, then it experiences the processing delay, then the propagation, and then the queuing delay. No one says A? Okay, good. How about B? Okay, that's also good. How about C? This is very good. Yeah, that's the correct answer. Processing, remember, when the packet comes in, the first thing that the node wants to do is look at the destination address, right? Because it needs to find out which is the outgoing transmission link it should send this packet to. So the processing delay is the first thing. If you can't process the packet, you don't know where to send. So if you scan this, there is only one option that starts with processing. Perhaps you can avoid reading the rest of it and just look for the processing. But I can make it more challenging having multiple that starts with processing, for example. This is just to have a discussion, just to gauge your understanding, but it seems that you understood it very well. So now I think this is good. You just need to do more practice, but if you have any questions, you can go to Ed Forum and ask questions without worrying about is a good question, bad question. There is no bad questions. I answer all questions. Right, that leads us to packet loss. Remember, I also said that this delay and this queuing is a problem. At the end, there may not be any space in the queue, and you'll be lost. So it's like waitlisted. A lot of students are waitlisted at the moment. I get so many emails that I want to take this course, but I'm waitlisted. You are in the buffer or in the queue. They're processing as the space are available, and they are letting you in, right? but also we don't want to have 2,000 students in the waitlist. We have only a few places in the waitlist. It means that the students will not be able to take certain things at some times. So the problem is packet loss is is not something that is unusual, and I have already told you there will be millions of packets lost before we finish this lecture. So you may wonder that how come the packets lost. So maybe let's take a couple of minutes and clear that confusion from our head. How come the packets are lost, and I'm so casual about it and saying millions of packets will be lost before this lecture is finished? And it's kind of, I'm saying it's okay, don't worry about it. How come? What if that packet is containing your bank account? How much money is left in your account? Would you be worried if that packet is lost? So how computer networks allow all these packets to be lost, and yet we don't have a problem because we use the bank all the time. Digital banking is the way to go. So what's happening here? Packets are lost, but how come we are not worried? Anyone, any idea? These are coming up topics in the few lectures. But any idea? Yes, there's a hand at the back. Can you speak up a little bit? Retry. Fantastic. So computer networks, later you will see that there are mechanisms to detect the packet has been lost. And when you can detect, then you can retransfer. So this falls under the huge umbrella of error control. Right? So error control you can avoid, or you can also detect and then recover. Right? So there are extensive mechanisms in the computer networking at many different layers: the detection, retransmission, avoidance. So at the end, there is no way your bank account information will be missed. Right? So I don't worry too much about the packet loss now. So I want to move on to explain you the throughput and the bottleneck.
It is well with my soul. I'm guessing the average throughput will just be the bottleneck's throughput.
So, but by now, you already understand that there are multiple links involved from end to end because it goes through multiple routers, right? So what happens to these links? These links are not the same. So this is the link speed RS, and this is RC. So if RS is less than RC, the question is, what is the average end-to-end throughput? So throughput means you are sending a large file from here, and you're receiving that file here. But when you're receiving the file at the right-hand side, or somewhere, it shows you what is the bits per second, effective bits per second, average bits per second you are experiencing, right? And it settles down to something. So the first one is saying if RS is less than RC, what will be the end-to-end throughput? RS is the speed of the link for the first one. RC is the speed of the link for the second one. So what will be the end-to-end throughput? RS, yes, because RS is the bottleneck. And similarly, if RS is greater than RC, then the answer will be RC. This is the weakest link, right? That becomes the bottleneck, and that's the maximum you can experience. So the lowest link will be what you will experience because you cannot overcome that. No matter how high connections you have for your own machine to the internet, right? You might have, subscribed to 1 gigabit per second link. Don't expect that you are going to get a throughput of 1 gigabit per second each time you browse the internet. Right? Because the internet is multiple links. Right. So I have a very simple question here. So what do I have? I have a big pipe in the internet, and although we show 1, 2, 3 links sharing this one, I'm actually telling you that there are 10 links. 10 connections fairly share backbone bottleneck link R bits per second. So there is a high-speed link in the internet, but there are 10 connections currently fairly sharing, fairly. So each connection is getting R over 10. Now the question is, if these servers are connected to the internet with RS capacity, and these clients are connected to the internet with RC capacity, then what will be the end-to-end throughput? Usually the server speeds are higher. RS would be greater than RC. But you cannot just now say that, the bottleneck would be RC. The client, RC is smaller than RS, so RC is the bottleneck, so RC is the end-to-end. So, but you cannot say that anymore if it's going through the internet, because it's going through this internet, and that link is shared by 10 connections, right? Fairly, it means you can get only R over 10. You are one of the 10 connections, so you cannot get more than R over 10. Now, if this R over 10 is smaller than RC and RS, that's the end-to-end throughput you are going to get. So in this case, it's not just the client's connection to the internet and the server's connection to the internet that determines your end-to-end throughput. Is the intermediate internet link that also, and at that time, the amount of active users in that link. So you can see that end-to-end throughput is something that you cannot forecast because you do not have a mathematical deterministic like circuit switching. In circuit switching, you can. The TV network, they can't. They have to, because the way they design their transmission, if they do not get that capacity, they cannot encode that MPEG video into that circuit, right? So they need to know those things. But in computer network, we don't do that. Computer network is totally indeterministic, stochastic, and on demand, and it's just the day. Okay, on that day, what you get, right? But largely it works, as you know. The internet is working, right? I'm using the internet to deliver this lecture. use the data in the computer network. It's not like a television net. Like everything is deterministic. We can tolerate packet loss.
What?
We can tolerate delay.
Was this Shulam?
So all these things can be tolerated in computer networking. So that's why it can be so robust despite all these uncertainties. And that made the internet the success. And in the beginning, I mean, beginning means before 96, when it was only in the hands of us, means computer scientists, and some electrical engineers. There was significant doubt that this internet could be used for voice and video. They were trying to build a completely different network called asynchronous transfer mode network, ATM networks. If you look at the books that I managed to write, my first book was on ATM networks. But it died as soon as I finished my PhD. But luckily, I didn't lose my job because I also believed in internet protocols. So I quickly switched to internet protocols. And then I saw, and we all saw, the whole world, that internet protocol is indeterministic, best effort, doesn't guarantee anything. However, it's very robust. Do you know how internet was designed in the first place? Can anyone tell me the beginning, the motivation, the birth of the internet? Why was it designed? Yes, at the end. Yep, fantastic. It doesn't have to be nuclear attack, but in the event that some transmission towers are destroyed in the war, the packet should still reach the destination. That's the goal. Find out a solution, right? That's what the defense does. They have funding, open funding, check. They have a big problem. The scientists are asked to find a solution. And the simple solution was packet switching. Everything also is circuit switching. Circuit means once you have the step in the circuit, if a transmission tower is destroyed, the circuit is broken. Everything fails. Packet switching, every packet contains the destination. So that tower is destroyed, so what? They will forward it through the other transmission towers. So it will still reach the destination. That was the power of the packet switching network, the internet. And this is what made it survive until now. And it looks like it's going to be with us for some time because everything has been ported onto the internet. Voice, telephone, no matter you pick up those.
What? Okay, yeah, no, whatever. Frick. How many hours is this? 3 hours. Frick me.
So this is the plan for week 2. We have 2 hours here today. We don't have to finish everything, but we'll make a start with the application layer, the application HTTP, and then leave the performance evaluation and the techniques for the next 2 hours on Thursday. I just want to remind you a few things. Lab starts from week 2. So this is week 2, and this is where you have to actually do the labs and work out all the questions and submit the reports to your lab instructor so they can mark them and give you the marks for the labs. So make sure that you attend the right labs, the slot that you are enrolled in, so you have a line of communication with your tutors. The tutors have designated students, and they try to focus on their own students, so make sure that you have a good communication line with your own tutor. The lectures, you are highly encouraged to attend the in-person lectures, so you have the opportunity to interact and engage, which gets recorded later, and those who do not attend will not have the opportunity to ask questions or shape the lectures. So as you have noticed that I give plenty of opportunities to my students to ask questions and elaborate on things that were not very clear. So this is your opportunity to shape the lecture. The face-to-face lectures are open to everyone. We have empty spaces. Actually, you can see there's quite a few empty spaces here, so we won't have any problem. The lecture recordings are available in Eco 360. This is the recorded from the university, the video. We are also trying to make it available on YouTube. I just checked before coming, it's working. The YouTube channel is linked to your web CMS, so it means that you do not have to be logged into Moodle if you are, in a difficult situation and don't want to, or don't have to, then you can still access directly from YouTube. For the Eco 360, you need to be logged into Moodle. I have also noticed that quite a few of you are already using Ed Forum, which is very, very useful because you can't ask all the questions here, or when you are reading later after the lecture, some questions come up and you want to clarify, then you just jump in Ed Forum, ask a question, and we try to answer within 24 hours, right? So if you have not used Ed Forum, I highly encourage you to go and see what's happening in Ed Forum. But remember that you have to join first. You can join yourself. We have given you the link. Today I have posted a welcome summary message of what I've just said in Web CMS. So just go and check it. It should be emailed to you directly. Okay, without further ado, I just want to get on with the lecture. But I just wanted to remind you that if you have any questions at any point, just raise your hand and I'll get back to you at an appropriate time. Right? So you have the freedom to stop me, ask any questions at any time. But I will also stop myself because I know the difficult areas, difficult points where the students need more clarifications and seek your input and see how we go. We also have a quiz sometimes, so we will have plenty of opportunities to stop and reflect about the topics. Okay, so without further ado, let me start. The very, very important, and if you like, is the famous concept in computer networking. So what is it? What is this famous concept? It's the layers. So you go to a wedding and you see the layer cake, and you all like the layer cake. All sorts of layers, different kinds of flavors, all coming to you at the same time. So this is kind of enticing you with the layer concept. But this is very, very useful, you'll see later. But let me first explain what we are talking about. So this picture shows too many layers. So the first thing I'm going to do is reduce it to 5 layers. Right? So if you look at the practical computer networks, like the internet, you'll see there are only 5 layers. So how I'm going to... Okay, so this is actually one layer. This is the application layer. So here is actually one layer. This is email is the name of the application that we use, an email, for example. And this is the name of the protocol. So this is like the protocol, and this is the name of the application. Right? So that's the application, that's at the top. Here notice one thing in your textbook, it says top-down approach. So where does it come from? It comes from this layered architecture. This starts from the top, and at the top you have the application. And then you have the transport. So this is the transport layer. And then you have the network layer. So let me just explain them. Just point to them, to the right one, and then I'll explain. So link layer, again, it shows 2 layers. Again, this is the name of the actual technology, like Ethernet, TCP. And these are like medium access control, which will be clear to you later. Shown in 2 layers, but it's actually the same layer, right? Those are like sub-layers if you want, but I just want to get 5-layer concept here. The physical is like twisted pair, copper, fiber optic. These are the things we talked about ESL cable in the first lecture. So that's the physical layer. They are all different kinds of technologies, but they are like at the bottom. You worry about them at the end. Start from the top application, and then you go to the bottom. So let's start counting arrows. Count the arrows, then you'll see there are 5 layers. 1, 2, 3, 4, and 5 layers. Okay. Why it looks like an hourglass? So this shape is unmistakable, right? We can't avoid this. Look, you look at this and you see it's an hourglass. So in many books and in many literature, they like to show it as an hourglass. So it's not about time the sands are going through. It's about the shape. The reason is this. If you list all the applications, then you will see there's a huge list of options, right? You have email, DNS, web server, and you just name it. We just keep adding new applications because computer network is a huge platform to deliver services, digital services, by writing a new application. Then you go to the transport, there's only 2 choices. And you'll see later we'll study TCP and UDP. These are very famous transport protocols. There's actually more options. Another one is TCP, but we are not going to go into that. Only 2 options. So that's why the hourglass goes like that. And when we go to the network layer, you can see there's a single one, internet protocol. Actually, there's 2 versions, version 4 and 6, but at the moment, 99% of the transactions are happening on IPv4. So as a first class, as a first introductory lecture, an introductory course in computer networking, we stick to IP version 4. Right? So when we say IP, it's only one choice. This is also the strength of computer networking because everything is done through the single protocol, internet protocol. So you can have very efficient hardware and very efficient software that only has to deal with IP in the backbone of the network. So all the traffic, whether it's Netflix, whether it's email, web browsing,
Skype? What else? Correspondent. Transport. Process data.
Can have very efficient hardware and very efficient software that only has to deal with IP in the backbone of the network. So all the traffic, whether it's Netflix, whether it's email, web browsing, they all at the end will create a single type of packet called Internet Protocol packet. And if you build a router, then it has to deal with this single type of packet. So that's why it's very efficient, and that's why it looks like hourglass. So hourglass has this top half. So what's happening at the bottom half? Why then it's again widening? So after that, we again have lots of choices. For example, if you go to the physical layer, there's so many choices. Like we have copper, we have cable, coax cable, we have fiber optic, we have wireless, we have satellite. So these options allow you to transmit data at the physical layer in many different speeds, efficiencies, reliability, flexibility. For example, in wireless, you see the transmissions happening wirelessly, so it allows me to be mobile, right? On the other hand, if you have fiber optic, then you can have terabits per second connection, huge speed and huge reliability. So if you're transmitting, terabytes of information from one continent to the other continent, then it's better to have a fiber optic under ocean and then send all of them nicely and then let them move around and transmit them through wireless, for example, right? So you need these kind of varieties, and that's why it becomes an hourglass. At the bottom also lots of options, right? So this is the protocol stack. Sometimes it's called protocol stack because these protocols stack on top of each other. And this is a very significant concept in computer networking because we study, as you see, week by week, layer by layer, right? We start with application layer in week 2. We try to finish application layer in week 3. Then in week 4, we move on to transport. Week 5, we move on to IP. So this is how our weeks will go, right? And there are a few other things about the layering concept that you have to be aware of. One of them is every layer is not just stacked on top of each other like the wedding cake. Wedding cake is just for you to consume, right? Here, it has to function. It has to provide reliable transmission capabilities for emails, voice, video, right? So each layer requires some support, some functional services from the layer bottom of it. So it assumes that the lower layer will take care of something. So let me focus on only these things. Right? So this is the idea of the layering, and that's why if you come to the transport layer, then you will see it has to provide certain services to the application layer. And if you're writing an application for the internet, if you're an application programmer, then you need to know what kind of transport layers are available in the internet, what kind of services they can give me, so I can write the appropriate application and invoke the right transport layer. So this is the first point. If you still need motivation why we have this layering, then this is a very good picture. This picture and this picture. So slide 4 and slide 5. Slide 4, slide 5. Which one is more complex? 4, 5. 4 is more complex, right? And who can tell me why you think this is more complex? Anyone want to share why this one is more complex than the? I can explain it, but I would like to know if you can say anything.
There's a many-to-many relationship.
Yep. That's precisely it. This many-to-many relationship. I think what he's going to say is this. if you write SSH, by the way, is a remote login. You use it all the time to access another computer, right? HTTP web services, Skype is for voice communications. But look at this transmission media. So transmission media, you have a lot of options, and you have many applications. So if you want to make sure, so this picture is about when you do not use layering concept, but you build the system as a monolithic, single layer, huge software. Then this SSH, you have to write it so that it can work with fiber optic, it can work with Ethernet, it can work with wireless, it can work with cable, because it's a single system. It doesn't have the layering concept, so it doesn't have the support of another layer to convert this information into the right physical layer. You have to do everything yourself. So you can see your application becomes very complicated. Similarly, if you write a web browser, HTTP, that web browser needs to make sure that it can run on Ethernet, run on wireless, it can run on cable. So that's why this is very complex. And if you use the layering concept, as you have correctly understood, that this is much more simpler. As you can see, you rely on the transport layer. For example, later you see that TCP is a reliable transport layer. It means if you write an application, and if you call TCP, you're operating system to transmit your data, then it's not your headache how the data will be reliably transmitted to the other end, whether it's going over Ethernet, wireless, satellite, under-oceanic cable. It's not your headache, right? You just focus on the application. Application may be a web service, so you focus on what the user data should be, what should be the response time to the user. You just focus on the user side and the application performance. So these two pictures, slide 4 and slide 5, shows you that using this layering concept, how efficient it becomes to develop software for computer networking. And that's why this layering concept is so important, so significant. And so widely used by all the developers in the industry. And in fact, this is the standard. So we'll talk about the standards a little bit today, because everything has to follow these standards. Otherwise, internet will collapse, because internet is a very interesting network, which is not a network, but it's a network of networks, right? So it connects networks for many different organizations. It connects devices manufactured by many different manufacturers. It connects all types of devices, smartphone, laptop, big supercomputers. So all these things need to work together seamlessly to give you the flavor as if it was done by a single programmer, written by a huge software, which is not. And that's why the standards are very important. So if everybody follows the standards, you know that everyone can communicate with each other very well. Okay, so far so good. I don't see any hands, so I don't have to worry about anything at this point of time. But if you have any questions, you can always ask. This slide is saying, is layering harmful? Because in the last 10 minutes, I only talked about the good things about the layering. You know, how great it is to have layering, how it makes things simplified, why layering is a great way to implement networks of networks, the huge internet, right? But is layering harmful? This is also useful for you to know that there are some drawbacks. And you never know. You have to deal with certain applications, some specialized applications where you might have to violate some layering principles, and you'll see some practical examples where the layering concept is violated for convenience, for security, for some real demand from the industry, from the user. So what could be the disadvantages of the layering concept? So this slide tries to explain some of them, and let's examine and have a discussion. The first one is saying that some of the functionalities might be duplicated, and later you'll see that one of the functions that gets duplicated is the error control, right? So every layer, tries to provide some sort of reliability, right? And then you'll see that this function is replicated. Then the idea of layering, as we said, that you don't want to worry about the lower layer, right? You just want that functionality. So it means that the lower layer will have to hide how it operates. The hiding the information sometimes can be harmful. For example, the reason the packet was dropped is hidden. So it may not be the congestion, and later you'll see that if the packet is dropped, the upper layer thinks, oh, the network might be congested, my data is getting lost, maybe reduce my rate, right? But maybe it was not because the network was congested, but there was an error in the bit. It was a wireless link, and the bit was flipped from 1 to 0 because it's difficult in wireless to reliably detect the symbols. In that case, you don't need to really reduce your rate, you need some other kind of error control, right? But you don't know, because the lower layer is not telling you all the information, it's hiding its operation, right? It's trying to give you a smooth interface. Header. It's very interesting that I'll show you later a picture of encapsulations and decapsulations. Every protocol layer needs a header of its own.
It's not hobby.
I'll explain that later. But if you do that, you'll see 54 bytes of header can be added very quickly in this 5-layer internet protocols.
No. Okay, at least the timestamp
Every
was saved.
protocol layer needs a header of its own. Right? I'll explain that later. But if you do that, you'll see 54 bytes of header can be added very quickly in this 5-layer internet protocol stack. 54 bytes of header. And this can be really painful depending on application. So I will ask you a quick question. Since you are all using SSH, log in, you have a secure connection to the CSC server, who can tell me that how many bytes the application SSH, I know that we have not covered SSH in details yet, but I'm just trying to see if you can answer this question. How many bytes your SSH application needs to transmit at a time? You are a client, you are using your laptop, you have an SSH connection, right? SSH means everything you're typing is going to the remote server, and it gives you a feeling, it's a window, as if you are sitting in that remote server, right? You are using the remote server. Everything you type, you can also see. My question is, how many bytes you need to transmit at a time? Yes? It's just one. Exactly correct. Each time you hit something on your keyboard, it's an ASCII character of that keyboard, right? It may be A, it may be B, it's R, whatever it is. That's an ASCII character. That needs to be transmitted immediately to the server. And the server needs to just echo that back. Yes, this is what you have typed. And then it shows you, oh, this is what I have typed. You know, this is SSH, 1 byte at a time. Because you want to replicate the experience that you are actually sitting at the keyboard of this server. You are typing at the keyboard of the server, not at the keyboard of your laptop. That's what SSH is, SSH or hard login or other kind of application. And that's why sometimes you might have seen that the response is a bit slow. You're typing faster than you can see. Because they are not coming back. But my question here, no, my discussion here is 54 bytes. So you type that, this is a single byte. You want to transmit from the application to the copper wire. You have to go through all the layers. Every layer has a header. And 54 bytes will be added to this 1 byte. So 55 bytes. Only 1 byte is the user information. 54 of them coming from this layering concept in computer networking. The layering concept is the situation. So that can be harmful sometimes. Right? Okay, layering violation you'll see later when you study network address cancellation. And as I say, sometimes you do want to violate the layering principle. But I think enough of that. If you have any questions, I'm happy to answer that. Yes. Yes. It's standard, and it's 7 bits. So we don't have 7 bits. Sometimes there are some universal encoding, you even code that 8 bits, but it's never more than 8 bits. Another question, maybe I'll use the problem is with the recording, you guys don't record unless I repeat it.
SSH is an edge case. Very few applications will send 1 byte at a time. Most will send a lot more. And even with SSH, you can receive a lot more as return. So it's a price to pay, but it's not always that inefficient.
Yeah, correct. Yeah. So this was an exceptional case, but in reality, this 54 byte will be amortized over many bytes of user information that you send. So if you send 1,000 bytes, for example, file transfer, you want to make the package as large as possible. Because of this, you want to amortize the cost of header over the data that you are transmitting. Right? So yeah, this is a good observation. Okay, so that was a good discussion. What I want to show you, you can read these things, but I need pictures. Okay? So this picture, I can use this picture to explain quite a few things. So what do we see here? So you see a typical internet where there are 2 hosts. They may be in 2 different continents. They may be in the same local area network, in the same department, doesn't matter. They're trying to communicate with each other using this recently discussed layering concept. Right? So I want to show how the layering concept is used in practice and what sort of dynamics we have. And which devices need to implement which layers. Right? Okay, so that's easy. We start with this example HTTP, which is the web browsing, right? So this one wants to send, for example, a GET. Right? You'll see it shortly after the break. We'll study HTTP, and it should return a response, right? But of course, how do you send this get data? I mean, how do you get to the host? I mean, here we are talking, so I just talk and you use your ears to listen to me. But in the internet, it has to go to so many different devices until it reaches to this destination, which may be in another continent, for example. So there's no way it can directly talk. They are not in the same room. So it has to follow the layered architecture of the internet. So actually, what happens is it goes to, like this, it goes downward, top-down approach from application to the transport. In this case, it's TCP. TCP is a reliable transport protocol, as you will see very shortly. And the TCP takes this get message and say that don't worry about it. Okay, just give it to me, and I know how to transmit this information reliably to the TCP of the other end, right? Then TCP actually doesn't do much. TCP gives that to IP, and IP says, okay, give it to me. I'm going to send it through all the routers, so it finds, at least one router, which will go to the next level, then find another router, and another router, until it reaches the router of that network, right? And we'll study all these functionalities. They are forwarding, routing, and all sorts of things. Then IP sends it to the physical layer, right? Actually, there's a data link layer, but we skipped. And then, this is the data link layer, Ethernet. In this case, we are using Ethernet. So Ethernet interface is in your hardware. So whether you have a laptop or a desktop, they have these Ethernet cards or wireless. There's another kind of network interface card. This is the physical layer. So this may be fiber, for example. So fiber. And then it doesn't go to the host, it goes to an intermediate router. Internet is full of these intermediate routers. Cisco is a huge dominant company which manufactures these routers and switches in the internet. Like they claim that if you type something, the chances are that it will go to a Cisco device. 80% of the traffic of the internet protocol goes to Cisco router. Now, this router, which is close to you, which connects your network to the internet, for example, you will receive this packet using this fiber optic in this case, because there's a fiber optic link, for example. But interestingly, this router doesn't implement TCP. Doesn't implement HTTP. It implements only Internet protocol. And of course, it has to implement Ethernet because it has to understand the Ethernet. So, 2 points. First, the communication physically goes downwards, not horizontal. Horizontal is a logical communication. But the physical communication of your data happens vertical, downwards, until it hits the physical layer. Second point, the layers, not all the layers are implemented in all types of devices in the Internet. Some devices, like the routers and switches, implement only up to IP, Internet protocol. Now at this point, I will go back to the previous slide because I want to use numbers now, because you see in the literature when you search, you will find lots of places where they use numbers. What is this number? So I will now number them. Remember I said that I want to get this 5-layer protocol. Sorry, I will start. Never mind. I just wanted to say that this is layer 1, right? Layer 2, layer 4, right? At some places you will see that they say layer 3 devices. Then you wonder, what is layer 3 devices? Right? So at least you can come back to this slide and you can say, oh, layer 3 devices means that you can understand up to Internet protocol. At some lectures, we'll talk about layer 2 devices. What do we mean? We mean that it doesn't have the capability to understand IP packets. It goes up to layer 2, and that's all it can do. So it can do Ethernet. So you see there's lots of Ethernet switches we have, like in this campus. They are hidden in the communications closets. But we need them. We don't always need routers. So if you have layer 2 switches, Ethernet switches, they will not implement all the layers. They will implement only the physical, and they will implement the liquid. Right? Okay, so that's the second concept. Going back to this famous picture, layered architecture, you can see, here you don't see the switches, but you see the routers, the IP. So now you can see the data will go like this, the data will go like that. So it remains in IP. So your get message is not seen by the router sends it to the next router, it goes to the IP layer, so IP has the address for the destination, so they can find the next hop. Then it reaches there, then at the host, it's a destination host. It can be a laptop, it can be an iPad, it can be a desktop. It will have all the layers because it's an end device, right? You have to have the right operating system, Mac operating system, Windows, whatever. So the operating system will have to implement all the layers, otherwise they can't release the operating system. It will be useless. It has to interpret, and this is the encapsulation, I will show you later, all the way to its HTTP server, and then the HTTP will understand, oh, I have just received a GET message, so I have to respond, and it will create this response. And then it will do the same. It will push it down to its TCP, and it will go back this way. And that's how you get the response. Is that clear? Any questions so far? Yes? Very good question. Let me repeat it because you were not on microphone. The question is there any device that implements up to transport layer but doesn't implement the application layer? Yeah, it's a good question, and the answer is no. I have not seen any device that goes all the way to the transport and says, I'm not going to support you in the application. Yeah, it's a very good question because you see that the applications and transport are like very highly coupled layers. If you're writing an application, and many of you, when you graduate, you will be dealing with applications because the bulk of our students go into developing the application software. Then many of our students, they go into the other communication software that they have to know the TCP IP, and many go to satellite and other kinds of, and we have to deal with all these things, whole protocol stack, wireless, mobile, cellular, and things like that. But if you're writing an application layer, the first thing you have to decide, do I want TCP or UDP? Right? You need the services of TCP or UDP. Why? I'll explain that very soon. But just to answer this question from the student, if you're writing an application, you need the support of the transport layer. And that's why the transport layer is kind of like, wherever you need to write the application, you have to put the transport layer. So if you have the transport layer, you will have the application layer as well. Because you have to support the standard applications such as email, web browsing, HTTP, and a few others. Okay. Right, so far so good. We have dealt with, now you can see why I went quickly to that picture, because then I can skip all of these slides which you can read. You can read the textbook. But as far as I'm concerned, I think we got those messages across. The layer concept going downwards and the multiple communication horizontally. Right? What I'm showing you here is going back to this layering concept, but here I wanted to show you the concept of encapsulation and decapsulation. We touched on that when we discussed about the 54 bytes added to your single byte of ASCII character for the SSH application, and you may be wondering why 54. So this slide will answer that question. As you can see here, so how many of you know about babushka dolls? Can you raise your hand? Babushka dolls. Okay, most of you. Great. Russian dolls, you can go and buy them. When I was a kid, I was fascinated by babushka dolls. Probably that's what led me to study computer networking.
What?
When I opened the babushka doll, I see another doll, and I was wondering what's
happening?
going on, and then my mom says, okay, why don't you open that one as well? I opened that one, another babushka doll comes in, and it keeps going like that, but it stopped after a while. You know, there's a physical limit that you can go. So in our case, if you like, computer networking is a babushka doll with 5 layers. Means you can open it 5 times. Each time you open, you get a header and you get a payload. But that's not from the same layer, it's from a different layer. But every layer wants to provide some services. And you'll see later very soon that in computer networking, the services can only be provided through the headers. So header is always the intelligence, right? And the rest of the body is controlled by the header. In packets, the header, you have to design the fields very carefully. For example, if you want to provide reliable service, in the header you have to have CRC checks. So it can check the packet payload to see if there was an error, right? So every layer wants to provide some services, so they design their own header. So the headers are necessary, but they're different in different layers. It doesn't matter. You need them. So now, if you go down, application, you send a message. This is maybe SSH, a single byte, right? But when this application wants to send it, it has to use a transport layer. And transport layer will say, oh, okay, you want to send this message? This will be the payload of my packet. But I have to add my header because I want to provide reliable service, right? For example, you are a TCP, and you want to say that I want to add a sequence number to this packet. So the other one can keep track of which packet was it. I'm sending so many packets, and which packet I should retransmit, for example. So you need sequence number, you need CRC, you need this and that. So TCP, we'll study TCP, which is one of the most complex software in computer networking later. Network layer will add its own header, link layer will add its own header, physical layer will add its own header. We are not showing too much about the physical layer. It's electrical engineering, it's very complex. So that's where you can see quickly you can get 54 bytes because TCP will have 20, IP will have 20, the link layer, depending on it, you will have some. But this process is called encapsulation. So this is where you reduce the babushka doll to cell, the big one. This is your application layer. This one is your transport layer. And then finally you have this. This is encapsulated, right? And this is the opposite. This is decapsulation. So it allows me to write something. there is something called decapsulation. So if you can say encapsulation, you have to do the decapsulation at the receiving end. And then you get the message back. Right? Is it clear? So this seems trivial, but it's important to get it right in the beginning, because this layering concept is very, very fundamental and very, very important in computer networking, which you do not see in many other places. When you're just writing a software which has nothing to do with the computer networking, standalone software, then you may not worry about these things. But if you are writing a communication software, or you want to write an application for the internet which has to do with other entities, then it's important to understand this concept. And this lecture is about theory, about the concept. Put it into your mind so you know the theories behind them. And once you work in the industry, you won't have time. Believe me, I deal with many industry people. They come here for degrees, or they come for developing new technologies. One thing is common, they say that they don't have time to think beyond what they're doing because the time doesn't allow them. They have to meet the deadlines to produce the software. And this is the time you can ask any questions, and your mind is free. So I want you to understand these things very well. So I could ask you many questions from this layering, because we covered many significant small topics in layering. I emphasized all of them here. But I will just ask one question to wrap it up, just to see how we are doing. So just one quiz from the layering. So this question asks specifically for two benefits. So it's a multiple choice test, but we are asking specifically for two benefits. So who can tell me, out of A to E, which are the two benefits that you get when you use this layered network architecture? You can have a quick discussion, because I will explain later why the others are not possible.
A, makes it easy to use new protocols.
Okay.
And D, prevents technology one layer from affecting other layers.
Okay. I will not say whether he is right or wrong, because I want to see more answers. So anyone who doesn't agree with him, want to say anything else? Or other option, you say, we all agree with him, so you don't have to worry about it. Or is there anyone who thinks that the answers can be different? It's okay, it's just a lecture. It's not the exam. So everyone agrees. That's good. All right, no problem. So let's have a quick discussion. So what did he say? He said A and B. Okay. So let's see if he's correct, first of all, right? We are just telling you that, yep, that's correct. What does A say? That it makes it easy to introduce new protocol. Is that true? Why? So you are nodding. Can you tell me, no, is this okay to nod? Don't worry about it. Why do you think that it's easy to introduce a new protocol if I have a layered architecture? Yes, I think you are in the right direction. To articulate it better is that if I want to introduce a new protocol, I have to worry about that layer only, the functionalities of that layer. So it's a new protocol for application layer, so I have to worry about the application layer functionalities only. Right? I don't have to worry about this huge monolithic software to be developed for this application. So that's why it's easier to introduce new applications, new transport protocols, new things in the computer network, new protocols. So I would say this answer is correct. A is correct, right? Okay, we agree. He also said D is correct. So let's first see if it is correct. It says it prevents technology in one layer from affecting other layers. Is that correct? Yes. So who wants to tell me why it is correct? Why prevents technology in one layer from affecting other layers? Yes? Because it's independent. Yes, precisely. So we talked about the layers. They are independent. They have interface to communicate with the layers above them, interface to communicate with the layers below them, but in the middle they have the details of their technology. So anything you develop there in the middle will not affect unless you change the interface. But you cannot change the interface because standardized, right? But in between you go and you can develop anything. And many things you see, like Cisco, when they develop their routers are better performing than maybe their competitors. How? If everyone follows the standards, then everyone should be the same. Because there are many things in between which are not subject to standardization, right? There's a technology, and you can use caching, you can use this and that to minimize the latency, which you'll see I will be asking you to do in your assignment. By the way, the assignment is still developing, I'm expecting to release it later next week, where you can improve the performance by introducing your ideas, your new technologies, yet not violating the standards. So I would say, after this discussion, D is
That's a cool image. It's ARP. That looks ugly. This looks so much better. What the frick? That give me no watermark, man. This is a great image. Oh, that's a great image as well. Twisted pair. Beautiful. Internet protocol. Hourglass. No. Actually, let's just change to light mode. Oh baby, perfect. Oh, that still sucks on the eyes, honestly.
Right? Okay, so it looks like he got the answer right, but how about why the others are not correct? For example, B, it speeds up packet delivery. Why it's not correct? We say layering is great, it's so fundamental, and now you're saying it speeds up the packet delivery, and then we're saying, no, that's not true. How come? Yes. So it may be just a sensor. It's not a sensor. Yeah, it is a sensor. Yeah, I think I saw your hand. Yes, go ahead. Do you want the microphone? No? You can speak loud. Okay, as it goes through more layers, what's the problem with that? Time. Anything else? Size of the packet, like adding lots of like 54 bytes and then transmitting each of these bytes. Yes, there's another hand. Complexity of the system as well, because they are independent from each other, so they can only communicate between them using the standard interfaces. It's not a monolithic system where you can have shortcuts. So yes, okay, very good discussion. So I gathered three things. So one of them, the first person said that you have to invoke all of these layers. So the time, it takes time because the application has to call the TCP, and you'll see very soon in your labs that you have to call these library routines, sockets and things like that. In the operating system, they all introduce some sort of latency. So that's the first point. The second one was that you are adding lots of bytes to transmit a few bytes, right? In the extreme cases, 54 bytes for 1 byte. So all these add up, and at the end, you are sending them sequentially 1 bit at a time, no matter what communication system you have. So the packet transmission time will increase, right? So how can the layering concept speed up, right? It's opposite, right? And the other point we found is the complexity, right? If it was a monolithic, then it would be transmitted straight away through the hardware. But now it has to go through so many layers, so that's adds up the delay. So that's why B is not correct. But it seems that you are getting the points, whether you can articulate or not. Sometimes you can still get it right. It means you understood it. So that's the first point, and I'm happy about that. Why C is not correct? It allows you to have many different packet headers. That's not necessarily a benefit. That's right. Yes. Yeah, you can have many different packet headers, but that's not a benefit, correct? We got it. Okay, last one. It creates many acronyms. But that's true. You see, networking is notorious for acronyms. And some of my colleagues in other universities, when they start the lecture, they start with the acronym table. They say that, go and memorize it. And I say, why you ask them to do that? He said, because when they go to the industry, they only use the acronyms. They don't have time to actually spell out transmission control protocol. Hey, Mahbub, have you finished the first part of transmission control protocol? They just say, hey, how is your development going? Right? So TCP is one acronym. But there are more than 1,000 acronyms you'll accumulate by the time we finish. Right? This is not a benefit. That's why it's true, but it's not a benefit. Okay, so I think we all deserve a break because it's 11:03, 5 minutes. We come back here and we'll resume our lecture. Thank you. You are right, the smallest one.
Not like any programming, guys.
The smallest one is the application. Then you put it inside this one. So you take the small, we start with the smallest, then you put it in another one. So you are doing the encapsulation. But in decapsulation, you are right. Then you decapsulate. Yep. We start with the smallest and just bigger and bigger.
What is telnet? What's carriage return? Let's just make it level 2. Unmarked not to be included in the report. Unmarked not to be included in the report. Marked to include in your report. Wow. That's what makes it. Actually, no. It doesn't really matter. Cousin Fred has returned to us. What the? Submit source code. Include sample output in the report. Okay. Submit source code as a separate file. So we actually do some coding this time. Okay.
Okay, so we are going to continue and with this layering, but we'll start with application layer. So this week, week 2, we'll try to do 3 things. So the plan is to finish section 2.1 from your text, which is about the principles. Then we'll try to cover HTTP, web, and email, right? So at the end of the day, you have to develop these application programs, right? So once you get into the industry, it will be all coding, right? So in the lecture, I'm not going to teach you the actual coding which you learn in the lab, and then you have to do the assignment. There will be some support, some extra sessions from your tutors for Python, C, whatever, Java. But here, we'll try to focus on the theoretical concept behind programming the application there. So what you do if your application there, you don't go to the switch or the router. You develop it for your user device, such as an app for your mobile phone, laptop, desktop, and things like that. So that's what it means by end systems. This is the client device. I want you to see that we have this concept. This is a very famous concept in computer networking. This concept is called client, and it's called server. Client server is such a good client server. So you write the client software for your user device, and you run the server part of this application in the server. So that will be running in the server. So a few things. So the server is always running. So that piece of code that you write as a server, for example, web server. You want to support web services for your company, and there are many different web pages that should be ready for clients to come and browse the web pages, right? So you have to run that piece of code infinitely, continuously, 24/7. So that's a different way of writing. The client, on the other hand, comes up when the user wants to do something and then closes down when the user is done, right? So this client needs to communicate with the right server. So if you want to write an application called HTTP, then you have to write the client software, and the example is your browser, for example, Google Chrome. So somebody has to write Google Chrome, and Google Chrome is not the server, it's the client part of HTTP, right? So it implements the client standards of HTTP into the software. And the web server implements the server standards for the HTTP. So client server is very important, and any assignment we give you, you have to develop both pieces of software and demonstrate that they are communicating properly. So that's the first concept. And it will only become clear to you once you start to do it. So you need to get your hands dirty, and that's why the labs and assignments are there. I'm just telling you the concepts. Interestingly, although vast majority of the internet services that you see, use, or hear about are based on this client and server paradigm, there's a very small, specialized, very niche applications in the internet that do not follow this fundamental concept of client and server. And here we just want to give you an idea that they exist and how they are different than the traditional client server, so you are aware of them, because in future you don't know. Lots of times things are happening at the moment, and nobody can predict the future. So this is called peer-to-peer. So how is it different than client server? So there's lots of pictures here, but I can draw my own, very simple to explain this concept. So this is client 1. This is server. This is client 2. So in the traditional client-server paradigm, right, you write the client so that it always communicates with the server. You write the client so it always communicates with the server. So this is the conventional deployment. What is peer-to-peer? In peer-to-peer, you write the client software in a way so they can communicate directly. Right? So this is P2P. This is peer-to-peer. Directly. So you have to write the client so that it should expect a connection from another client, which is something you do not do in your browser, Chrome, right? You don't expect another user will connect to your Chrome and start downloading things from you. But in peer-to-peer you do. So there are some applications, and some of them are brewing. For example, blockchain, I don't know if you have heard of that. These are the distributed systems. So distributed systems may become popular in the future for many reasons. They can be very efficient. So that's peer-to-peer. There had been some applications, they were very popular in the past, BitTorrent, and another for music sharing and all these things. They had their problems. There were many regulations against them to stop them. So we don't know if they are going on underground. Maybe it's being used heavily, but we don't see them. But as a student of computer networking, you should be aware of it. Okay, so let's leave peer-to-peer. We might have a fraction of the lectures to cover that at some point. I don't know. I have to check the schedule. But let's go back and focus on the vast majority of the deployment in the internet we did client-server based. So the first concept in client-server is the process. So what is a process? I'm sure many of you are already aware of. Because you have to kill processes sometimes, right? If you're in the server and your process got stuck, what do? You kill it, right? How many of you killed a process? It's not a crime to kill a process. Okay, good. All right. So it's an operating system concept. You execute a piece of routine or software, that becomes a process, is running, right? You can run another process, right? You can run multiple processes at the same time in your operating system. So these days our operating systems are very powerful, and we can run hundreds of processes in a machine, right? Two processes need to communicate with each other because we are in computer networking. So we talk about communications, exchanging of messages. If you're an application programmer, you are writing a process for your application that will be running, right? And it needs to exchange messages with another process. That another process can be sitting right in the same computer, in the same operating system, or most often that process is sitting in another machine, in another operating system, far away from this computer. If it is sitting in the same computer, it is trivial. The communication between two processes is trivial because the same operating system has commands for you to exchange. It's called inter-process communication. Much easier. When the processes are sitting apart in the internet, far away, that's where it becomes a challenge. That's where the layering concept and all sorts of computer networking concepts come into play. So we'll mainly focus on not inter-process communication, which is within the operating system. We'll focus on processes in different hosts, and that's like message exchange between two processes in two computers. That's what we'll focus on. So that's about this slide. The next concept is called socket. It's so famous, right? If you want to do any kind of communications software development, then you have to know what is a socket. So it is an operating system construct. It's available in every operating system. So socket is like an interface between the application and the transport layer. Now remember, we talked about transport layer being always together with the application layer. And if you are an application programmer, then you need to know which transport layer I'm going to use in my operating system. And we also talked about the interface, and we also talked about that certain services provided by the transport layer to the application layer. So how do you provide this interface in a programming language concept when you are dealing with developing a software? So that's the concept of socket. So what is a socket? Socket is, as you can see in this picture, this is an interface between the application and the transport. Now interestingly, everything from transport to the physical layer is implemented in the operating system. So when you install the operating system, you are installing transport layer, you are installing IP layer, you are installing data link layer, and you are
Can you style images? Ooh. JPEG equals it. Oh, no way. No, they don't have it that way. Oh, I am correct at the game. I did light gray. Light gray's not a color. Light gray. Frick you. What? Yeah, no. Wait, that means I can just use the AR on net. Can I like delete things?
physical layer that is connected to your machine. So operating system has all the layers from transport and below. What it doesn't have is the application layer, because that's what you are writing, right? This is a software which sits on top of the operating system. That's the user space. That's the terminology that is used. Now, the socket is in between. So when you write an application layer, you can open a socket with your transport layer, and you can say, I want to send this message to that host. All you have to do is just dump it in that socket, right? And you can assume that it will be delivered to that process at the other end, right? So if that process is running in this machine or not, it doesn't matter. Anywhere in the internet, if that process is running, and if you can identify the process properly and tell the socket that please send this message to that process which is identified by this, and I'll explain how do we identify a process, then that socket will do the job for you. You know, it will simplify your life, right? And in this example, as you can see, we have a huge internet between these two machines, and yet they have no problem of exchanging messages if they are using socket. So this is a process running in this machine. This is a process running in this machine. This process will send some information in this socket and identify this process somehow, and it will go all the way to this process. So that's the power of sockets for writing application programs. And this is what you have to do in the lab, learn that socket programming. And we have given you snippets. If you go under lecture in WebCMS, lecture week 1, we have given you Python, C, Java, all the snippets. And it's not very difficult to implement, but you have to start playing with them. And in the assignment, you would need them. So, question is, how do I identify a process anywhere in the world? Because there can be practically millions of processes running in the internet. There are hundreds of millions of devices, and each device may be running multiple processes, right? So how do I identify uniquely a process in the internet so I can tell my socket, please send this message to that process? So my question, can I use the internet IP address? Is it sufficient to identify a process? Yes or no? Yes? No? No? Okay, no. Why no? The IP is unique, right? In the internet packet address is unique. So why can't I use IP to identify a process in the internet? Yeah, you said no. So yeah, why do I need a port? I mean, why it's not sufficient to have the IP address to identify uniquely a process in the internet? IP only identifies the host. And yeah, but what's the problem? Because the applications are running in the hosts. Yeah, I think what you are now getting at is you may be running multiple processes on the same host. So it's not sufficient. It's necessary, but not sufficient to reach to the right host. Once you reach to the right host, now you need to find out, oh, which process? I can see 100 processes running in this host. Where do I send it? So identification of a process requires two entities. One is a unique network address, which is the Internet Protocol address, 32-bit. But you need on top of that another one, and that is called port, as we mentioned somewhere, port number. So you'll see processes are identified by two. One is IP address, the other one is port. Now, interestingly, these port numbers are standardized for the standard services. example, if
Oh, they just have the image. What is input format? Huh.
If I say connect port number 80, it means that you are interested in HTTP. Because HTTP is standardized to run on port 80. So if I write a server code to run my web services, I cannot use 81. It will be foolish for me to use 81 because the rest of the world will not find my web pages. Because they will use 80 to reach me. And they will come here and they will see, oh, I don't see any 81 running. So if you are a programmer, a communication software programmer, you need to know the standard, right? So in this case, it's 80. If you're running a mail server, it is 25. So they have all sorts of different port numbers. So if you are developing an application layer protocol, so that's the third concept. What is a protocol, right? So protocol is, again, a standard language, right? So if I want to communicate with you here today, I have to use English, because otherwise I will get into trouble. Everybody may be talking different languages. But if we say, the lecture will be delivered in English, then we all switch to English. So here, the protocol has a standard. And why? What is it that the standard is trying to do? So this slide tells you a few things. It says that the types of messages exchanged. So it is a query message. It is a response message, right? So the protocol has to say it's a query message. Then the format is different. If it is a response message, the format is different. And it has to follow the standard so everybody can understand the response. Right? Then it says the syntax. What fields in messages and how fields are delineated. So you see that there are headers. We talked about the header. These headers are all standardized. So how many fields do you have in the header? What type of fields? What's the meaning of these fields? Right? So every application layer we have some fields. Then the semantic, the meaning of the information in the fields. And they say that when you generate what messages. So that has to be standardized as well. And talking about the standards, who knows what RFC stands for? It's another acronym. Yep. For comments. Fantastic. Request for comment. When I first heard it, it never occurred to me it's a standard. I thought it's just a request. You know, we request our colleagues all the time. Can you please comment on this? I was just trying to stop this. But it turns out that this is the standard. The reason is the historical reason. In the internet forum, they write these things. They have meetings 4 times a year, and they write the draft and then ask for comments. And now they call it internet draft. And once all the comments have been addressed, and they are happy to release it as a standard, they give it a number, RFC, blah, 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 and they say that this is the latest one, and sometimes this is an addition to another one, sometimes it supersedes the previous one, and these are all free, text-based, you can just search and you can download, nothing to pay for anything. But if you are a vendor manufacturing something, or if you're a vendor developing a communication software, you have to make sure that you understand these RFCs, You have downloaded the RFC and make sure that it's conformant to that RFC. Otherwise, it's not going to work in the internet, right? It will create confusion. So there is RFC for HTTP, RFC for SMTP, RFC for everything. Right? There are multiple RFCs for the same thing because they talk about different aspects of it. Sometimes they talk about the security of the protocol, sometimes they're talking about other enhancements and things like that. There are also lots of proprietary applications on the internet, right? So not everything is coming from RFCs. For example, Skype. A lot of people use it, but they don't see how exactly, it's not an open document, it's a proprietary document. Skype can change it anytime, and they don't care. It's totally controlled by Skype. So you have to go to Skype and download the latest software. You cannot write your Skype software, it's not open. Okay, so you can now, so that's the concept of the protocol. Right? And they have to deal with timing, data integrity, security, and things like that. So now this slide is talking about the transport. Remember I said that the application goes hand to hand with the transport. So this slide tells you a few things. You can see, before it goes to the transport, it talks about the transport services that you might need from the underlying transport layer if you're writing an application. So on the left-hand side, we have two examples. For example, file transfer is a huge application in the internet. We use it all the time because we have large files to download. We have software upgrades, and whenever you do upgrades, they're basically downloading the patches and the files and things like that. But what services it needs from the underlying transport layer? Right? So that's why we may not be sure, right? So this slide tells you it is file transfer. Then for the data loss, it needs no loss service. It needs a transport layer which can guarantee that if you send something to a socket, it will not be lost. It will be delivered with 100% guarantee to the other end. You need that service. Why? Because in file transfer, if a single byte is missing, that file is not considered complete. It is considered useless. Huge file, 1 byte missing, useless. But if you're doing streaming video, it's loss tolerant. So the service you need from the transport layer is something else, right? If you're writing a streaming video, loss is not the main thing you want. It can tolerate loss because it's designed for human consumption. If I'm watching a video, I'm more interested in the video quality. Do I understand that this is a soccer game? Can I see all the players? When there is a goal, I can see the goal, right? As long as I have this in high quality, good frame resolution, I don't really care if a single byte was lost in the transmission, right? So they might create a small problem in the video, but the consumption is for the human, it's for entertainment, right? It doesn't matter. However, it can be time sensitive, these applications, right? Sometimes milliseconds, sometimes seconds, it can tolerate, depending on the applications. And if your transport layer is taking too long to make sure that every byte can be transmitted with 100% reliability, it's not really good. That's not the transport layer you want for this application. So this slide shows you that if you're an application programmer, you need to first decide what type of services you need from the underneath. And based on that, you select the right socket, TCP socket or UDP socket, and in the future, in some operating system, SCTP socket, which we are not going to consider in this basic course. But you get the message. We are going to focus only on two types of transport services. At the left-hand side, you see TCP, and the right-hand side, UDP. So this is the lecture where we need to introduce these two. And in the later lectures, we'll delve deeper into UDP and deeper into TCP. But fundamentally, you have two options. In a sense, this is great because you don't have to worry about too many choices, but it's important to understand the difference. So as you can see, TCP has so many things. The reliable transport needs to give 100% guarantee that every single byte you jump into a socket will be delivered to the other socket, right? Flow control is very important, right? You're downloading a file in your small mobile phone from a supercomputer, The supercomputer is having to dump as much data as possible very quickly to you because it thinks that, I'm doing a great service. But it can overwhelm your operating system in a small device. So flow control means you use a kind of socket that can talk to each other to make sure that these two devices are in sync. No one is trying to overwhelm anyone. You have to give congestion control. The internet is so huge and millions of devices are dumping data into it. If you do not control the congestion in the high-speed backbone, then the packets will be waiting in the queue forever. Or, worse yet, they will overflow and they will be lost because the queue sizes are not infinite, as we have seen in the first lecture. So it's important to control the congestion. Who controls the congestion? Right? So in the normal transport network with the car driving, we have these nice traffic lights and all sorts of other kind of controls. Now in the computer network, you need something, which is very simple to deploy. If you make the routers, the intermediate hops, very complicated, then they will bring down the performance because they need to push traffic at gigabits per second speed. So the congestion control responsibility in the internet is not in the actual routers. If you like, is on the drivers. So the drivers need to make the decision. So here the drivers are your application programs. So TCP, if you use TCP, The TCP will make sure, TCP has very interesting intelligence, you'll see, to understand when the network is congested or not. And based on that, it will paste the data from your operating system. It's very complex software, but it's sitting at the end, yet it has a huge intelligence to understand the congestion state of the internet at that time for your route. And it controls that. So you can get so many services from the TCP, and that's why it's the most heavily used, and this is the most complex software, and we are going to spend most time with TCP than UDP. UDP will be much more simpler, as you can see. It is an unreliable, it doesn't provide reliability, it doesn't provide flow control, it doesn't provide congestion control, it doesn't have any guarantee, nothing. So if it doesn't provide nothing, why is that? When UDP can be an attractive option for you, yes? So can you speak up? Generally faster, yeah. Why UDP is faster? Yeah, less overhead. Because TCP has to deal with so many things, so of course it will be complex, it will be slower, right? UDP doesn't care if the byte has been received or not, so it can be very fast. It can transmit the next byte, just like that whenever it's ready. It's going to say, no, hang on, I want to see if the first byte was received or not. If not, I'm not going to send the second byte because you want 100% reliability. Yes? Yeah, very good observation. So what the student is saying is that when you're looking at the pros and cons, TCP is very reliable, but not necessarily very fast. Yes, it's correct observation. So UDP is very useful when you don't care about 100% guarantee of every single byte you are transmitting. You can tolerate some loss, but you want a very quick service. So you see that Skype and many other streaming video, they prefer to use UDP. As I said, that loss here and there in the video will not be even perceptible to the human, because we extract information in an entertainment video in a different way than a file transfer would extract the information from the byte stream. Right? So UDP has a place, and since the commercialization of the internet in 1996, there was a flurry of services on putting voice and video on the internet. Before that, internet was a data network transmitting computer information, but once it was commercialized, then everyone wanted to use it for different purposes as well, voice and video. And as soon as they started voice and video, they found out that TCP may not be the best choice, and then the UDP started to grow. But before that, if you do a Wireshark is a protocol inspection software that you'll be using in your lab, which can collect lots of data from the real network, and you can inspect the protocol field in the Wireshark, and you'll see whether it's TCP or UDP. So if you did it at that time, even 20 years ago, for example, you'll see that 90% of the packets that you are observing in the internet are saying that I'm a TCP packet. Only 10% UDP, and we are not using much UDP. But now it has changed, so in the lab, you might see that UDP is not just 5% or 10%. You might see there's a significant fraction of the traffic is UDP. Right? So UDP is also needed. So these are just two choices for you, and depending on what we ask you in the assignment, you have to use the TCP socket or you have to use the UDP socket, right? We have not finalized it yet, but it's coming up. Hopefully, we can finish a smaller version. Overview version will release it next week. Right, so these are the applications, these are the name of the protocols and the RFCs, and as you can see, the interesting thing is, so this is something that, although I spent a lot of time in the last slide, I didn't explain this. What is this, and what is it I have not explained? UDP or TCP. So whenever I say it's good for UDP, like telephony, right? A long time ago, telephony was you have to pick up the phone, but now telephony.
This should be here. Is this all a part of socket programming? I don't know. Application layer protocol define.
It uses all voice over IP, right? And then heavily into Unity, and then all the video heavily using Unity because they need the fast service. But now we are saying even the games and the telephony is TCP or UDP. It means that you could also somehow transmit this information using TCP, right? So you will see that in some cases it is possible to use TCP to download fraction of the video, for example. But if you do it right and control the delay in a pipeline manner, then you can still produce the video smoothly to the user, and the user doesn't know that you are using TCP. So some of the standards are switching to TCP. Very interesting, like video. You'll see that Netflix and many, they have switched to TCP. So they can, not because they love TCP and they hate UDP. It's because of very interesting reason that we will explain later, perhaps, down the track, but I can just tell you now, is because they want to reuse the infrastructure of web service. The web service was just for information, text information, but now say, oh, I can deliver video using the same web server, so I don't need a video server. But web server is based on HTTP. HTTP is based on TCP. So that's why they are using TCP. Question? Yeah, so it's a good question. The question is, can I use both both TCP and UDP, trying to take the best of the both worlds. The answer is yes or no. The actual data transfer has to be over TCP or UDP. You have to make a decision. But in many cases, you can use TCP for the control operations. So for any service, you need some user authentication or exchanging some other sideband, like side information, not the real video or the real application data. You use that for TCP, and when it comes to the real delivery, you can use UDP, for example. Yeah, great question. Okay, so if you have no other questions, I would like to do this quick TCP. So there is only one true statement here because we want to finish at 55. So who can, or this is just pick the true statement. So I will ask you, who thinks A is the true statement? We say TCP provides reliability and guarantees a minimum bandwidth. Do you think it's true? No one thinks it's true. How about B? TCP provides reliability while UDP provides bandwidth guarantees. Vehemently, no B. So it's not. TCP provides reliability. C. TCP provides reliability while UDP does not. All the hands are raised. So the correct answer is C. But I'll tell you why A is not correct. It seems like TCP provides reliability, so it guarantees the minimum bandwidth. But it doesn't. It doesn't. It guarantees 100% reliability for transmission of that packet, but not the bandwidth. You cannot say that I can transmit at 1 megabit per second. TCP cannot do that. UDP cannot do that. There is no protocol in the internet which can do that. Okay? The last one is incorrect. Neither TCP nor UDP provides reliability because we have just discussed that TCP provides reliability. So again, I see largely in general, I don't have any problem getting the message across. You are getting it right. However, I can ask many different questions, so I will give you some practice homework soon, so you can continue practicing them. I still have 2 minutes to just tell you the plan for the next 2 weeks. Okay, so the plan for the next 2 weeks, sorry, the next 2 hours in this week will be HTTP. So we'll have 2 hours, right? We'll try to finish HTTP and email. However, email, we are not going to spend a lot of time, but our focus will be on HTTP, right? So HTTP is a huge deployment in the internet at the moment. It started with servicing the web, and it was a huge success, still doing it, and now it is doing video, as I just told you. So the Netflix and the Amazon, they are all using HTTP, online shopping and everything. So we want to spend on HTTP, particularly we want to spend on the performance of HTTP. How do you analyze the performance? What are the developments happening in HTTP over time to improve the performance? So we will focus on those ones in the next 2 weeks, and we want to finish HTTP and email this week. So next week we move on to different.
Time to sleep. Good night.